Hello everyone and welcome to DhiNexus. I'm Oorja and in today's session we'll be learning about physical properties of alkyl and aryl. At DhiNexus we try to make learning simple, clear and engaging. So please stay tuned till the end of the session. Now, what all topics will be covered in this session? We will be looking at solubility, boiling point, melting points, polarity of both alkyl and aryl halides, dipole moments, and examples. Along with that, we'll be having a look at some of the NCERT questions. So, for whom will this particular video be helpful for? Anybody who is preparing for their board exams and they refer to NCERT. So, students from CBSE board and even IGCSE board can be benefited from this. Sometimes a couple of questions in IIT JEE or NEET exam come from this particular topic. So that will also be helpful if you learn about especially the polarity of alkyl halides and their dipole moments. The examples from NCERT questions can also be seen sometimes in the competitive exam. So let's get going. First topic is solubility. But if I just pause for a moment and talk about the general, how do we figure out that, a particular compound is haloalkane or not? Haloalkanes are sweet smelling substances and they are generally like the lower haloalkanes are liquid in nature. But as the size increases, they become gaseous in nature. So next is the solubility. Now, haloalkanes, they have, if I talk about CH3X, this is any haloalkane. The general formula of haloalkane is RX, right? Where R is my alkyl group. So this is my alkyl. And what is X here? This is the halide. It acquires a partial negative charge, so this will acquire a partial positive charge. Now, what is the reason for acquiring a partial negative charge? Nothing but the fact that halide is electronegative in nature. And my alkyl group, this is going to be electropositive in nature. So, as we can see, they are slightly polar. But despite this polarity, these are very slightly soluble in water. Water is also known to be soluble. So technically, my polar substances should dissolve in polar substances, but that is not observed in case of RX or my alkyl halides. The reason is nothing but the fact that when I'm dissolving alkyl halides in water, two things have to be done. Energy is to be required to overcome the attraction between already alkyl halide molecules. And bonds have to be broken. Which kind of bonds? Hydrogen bonds, which are formed between water molecules. But when you're breaking them and forming new bonds with alkyl halide and water, these bonds are quite weak. These are quite weak as compared to the H2O, between the hydrogen bonds between the already existing water molecules. So the energy that is released is quite low and weaker bonds are formed. Hence, the solubility in water is low. Both alkyl halides and aryl halides, however, are soluble in organic solvents. So what are my organic solvents? You can have C6H6. You can have ether. Ether is ROR. This is the German formula. Right? So they're both soluble in organic solvents because their polarity is quite low and organic solvents are also known to be non-polar. So you should always remember this concept of like dissolves like. The same polarity substances will dissolve together. Moving on, we have melting and boiling point. So generally, compared to our hydrocarbons, if I have a hydrocarbon, say C2H6, which is nothing but ethane. So compared to ethane, of course, my CH3Cl is going to be more polar, right? There will be more polarity. as we just saw. So the boiling point or melting points in such cases is observed to be a little bit higher. And if I talk about in the same, like for these cases, basically, if you have RF, RCl, RBr, and RI. So iodoalkane, bromoalkane, chloroalkane, and fluoroalkane, what will be the boiling point? What is observed? We observe that the iodoalkane, bromoalkane, chloroalkane, and fluoroalkane will have the higher boiling point in this case. And what is the reason for this? Some of you may think that RF bond is quite high, and hence there will be more bond in phthalate. But what is observed is that as the size increases, as the size of a haloalkane increases, suppose this is for RF, but for RI, which is iodoalkane, it is going to be bigger. So van der Waals forces increase, and hence we can see that iodoalkane has the most in this case, which will be iodomethane, then bromomethane, chloromethane, and fluoromethane. So this is the trend that we observe when we're talking about boiling. Suppose now if I have a different, for the same alkyl group, I'm just changing the number of halogens. In one case, I have CCl4, CFCl3, and so on. Now, again, the one which has more number of halide will have the higher boiling point. Reason being nothing but the fact that with the alkyl group, the halide ion will form stronger bonds as compared to with hydrogen. If I have, suppose I keep on increasing my alkyl chain, then also the boiling point would keep on increasing, as the molecular weight of the alkyl group is also contributing to the boiling point. An interesting point which is observed is when the isomeric haloalkanes are taken into consideration when we're talking about the boiling points. So what happens is, suppose I have what is the name of this compound? This will be called as chloropropane. And on the other hand, I have, in fact, let me take chlorobutane. So butane, that means 4 carbons. And on the other hand, I have this. What is this? Iso. Rather, this is what I should take. So, in which case am I going to find my boiling point to be the most? The boiling point will be higher for this one and not this one. The reason is that as my branching increases, my branch or side chain increases, the van der Waals forces between the carbon atoms decrease, and hence it is easier to break those bonds, which is why as the shape starts to appear like a sphere or that of a ball, the boiling point will lessen. In this case, let's take one more example. If I have something like this is a tertiary haloalkane. I have a secondary haloalkane here. And I have a primary haloalkane. So, such questions are often asked. Which one would have the highest boiling point? So, primary, then secondary, and then tertiary. As a shape starts to appear like a ball. Moving on, we also look at the boiling point of the aryl halides now. The trend is pretty much the same. Iodo group will have the most, bromo, then chloro, and fluoro. Reason being the same, that iodo group will have higher size, bigger size compared to rest of them. So the trend is like this when we're talking about the boiling. Now, comes a fact, for example, in the same aryl, you have two halogroups. This is the, you must know, if this is 1, 2, 3, 4, 5, and 6. My position 1, 2 is known as the ortho position. Position 1, 3 is meta, and 1, 4 is a para. So although the boiling point in all of these is pretty much the same, it is almost in the same. You can see 453 for ortho, 446 for Kelvin of meta and para. So these are not, there's not a high difference. But in case of para, what we've seen is that melting point is very high compared to that of meta and ortho. What is the reason? So it was observed that in case of melting point, the para group, para isomer, is fitting the crystallization properly. Like there is a proper symmetry to it. Proper symmetry is observed when the para isomer crystallizes. That's pretty clear. As we can see here, this would have a high symmetry. And if I'm trying to just dissect it, this one would have high symmetry. So in this case, my para has highest melting point, then comes meta and ortho, respectively. Meta is actually the least, and then comes ortho. So trend for melting point would be para, then ortho, and then meta. And for boiling point, it is ortho, then para, and then meta. What about polarity and dipole? Like I already said, that my haloalkanes, they are going to be polar, and the polarity is because of the high electronegative character of the halide ions. It takes the electrons towards itself and make the bonds polar. Same is the case when I have my aryl halides. These are also polar. Now, what about the dipole moment, especially in the case of my haloalkanes? What is observed is that, and this is a point of confusion for some students, CH3, CH3I, which one should have a higher dipole moment? Let's understand what is dipole moment. Dipole moment is a vector quantity which is denoted by mu, and it is the product of charge and the distance of separation, which is d. Its unit, please note, is capital D, which is short for dB. So, if I have polar bond, like in this case, I have a polar bond. So my since it's a vector quantity, so it would have both magnitude as well as direction. Now the arrow points towards that compound which has that atom which is more electronegative. So it will go towards halide because it is more electronegative, right? And the tail with a cross on it, like a plus sign, is retained with the electropositive. So if I talk about CH3F, please make sure that it is the product of both Q and D. Now, although yes, that fluorine atom has the highest electronegativity, so the charge is going to be there, but my distance of separation. Fluorine atom will tend to acquire a high amount of like a bond between carbon and halide fluoroatom is going to be short. But in the same case, if I have CH3I, the bond is going to be long. So since the bond is shorter in case of CH3F and it is a product of both Q and D, the dipole moment is higher for this. If I talk about aryl halides, there's one more thing actually we should know before we talk about aryl halides is that the fact if you have, for example, you have BeCl2. This is not alkyl halide example, but just to make you understand the concept about symmetry. My dipole moment would go in this direction. So what we're observing is that there is an equal and opposite movement of dipole. So in such a case, the dipole moment gets cancelled and we get a zero dipole moment. Similarly, here we have a high symmetry. The chloride ion will take the electron towards itself in both the cases and it will become highly symmetric. So dipole moment comes out to be zero. In this case, in ortho case, the dipole moment is coming out to be 2.54, which is the most. And for meta, it is coming out to be 1.7. So which one has the most? We have ortho, then meta, and then para. Such questions are highly asked when we're talking about NCERT related topic, or we're talking about sometimes we also observe this in competitive exams. So this is the dipole. What is the reason for this? See, as I already mentioned before, the dipole moment is nothing but a vector combination. So it follows parallelogram law of vector addition. So what is the formula of parallelogram law of vector addition? It is mu1 square is 2 mu 1 mu 2 into cos theta. Right? So we know that the value of cos 60 degree is, and what is the value of cos 120? It is half in case of cos 60 degree and minus half in case of 120. So for the ortho position, the angle which is formed between two chloride ions, that was seen to be 60 degree. Now, if I put it here, I'll get some value which will come out to be this one. But in case of my cos 120 degree, which is observed in case of meta, the value is minus. So this part actually becomes negative. If I just show you here for meta, it would be like this, mu1, mu2, and then you have minus half. So this would get cancelled and this quantity becomes negative. So definitely it is going to come out to be slightly less than ortho where the quantity is getting added. Right? So this is what the dipole moment trend is we're observing. Let's look at some NCERT questions. So the first question says that alkyl halides, though polar, are immiscible in water. We have also already seen in the first slide is that although haloalkanes are polar, yet they are very slightly soluble. The reason is nothing but the fact that solubility in case of water decreases because energy is required to overcome attraction between both alkyl halide bonds and you have to break the bonds between H2O molecules. And less energy is required when new bonds are formed between alkyl halides and water molecules. If less energy is released and weaker bonds are formed, then we say solubility is. Moving on, dichlorobenzene has higher melting point than ortho and meta isomer. So we have already observed the reason is the packing of crystallization of para isomer is, suppose this is my difluorobenzene. So in this case, my symmetry is the highest and hence the para difluorobenzene has higher weight. What about the dipole moment of CHCl3, CCl4 and CH2Cl? This is a very good question and we must discuss it separately. CHCl3, then you have CCl4 and CH2Cl4. So, in case of CHCl3, please note that all of these have a tetrahedral structure. So, what would the tetrahedral structure look like? I have chlorine here, hydrogen here, and chlorine here. And then I have CCl4. Please note that in case of a tetrahedral, the bond angle is 109.5 degrees. Here, observe. And so let's see. I have amongst carbon and chlorine, which one is more electronegative? Is going to be chlorine. So the arrow will point towards chlorine. Here, the arrow will point here. And among carbon and hydrogen, it is going to carbon with the arrow will point. Here we'll have it towards chlorine in all of these cases. And like this for CH2Cl. So let's first look at CCl4 because it is easier to see that the dipole moment in this one is going to be 0. Why? Because it is selected. The resultant of this one is of this upper part is going upwards, and all three of these is going to come down. Since the value is both equal and opposite, the dipole moment will become 0. And what happens in case of CHCl3? One of the dipole moment is pointing upwards, two are pointing downwards. I have this, and hydrogen is also getting added up here, and it's coming like this. This one is going to be slightly longer because chlorine and chlorine, two chlorine are downwards, pointing down. Right? So it is going to be slightly less, but the value won't be equal to 0. It will be there. At least dipole moment will be there, won't be equal to 0. What happens in case of CHCl? Two of my chlorine atoms, they are coming downwards, and to it my hydrogen is also contributing. And a partial of this one, carbon and hydrogen bond, is going in the up direction and slightly cancelling. But overall, you can see three of the dipole moments are going into the same direction. And in this case, only two dipole moments were coming in the same direction. So, dipole moment would be the highest for my CHCl2, CH2Cl2, then CHCl3, and then CCl. Now, this is a point of confusion for a lot of students. So, in dipole moment questions, what you're supposed to do is that you should always draw a figure and then try to locate where the bond will be going. If you found this video helpful, then you should all like it and please share it with your friends so that they can also gain some benefit from it, and please subscribe for future videos. Thank you and have a nice day.